Welcome all to MP3672. If you were in the class last week, you'll realise that with part of that linkage tutorial, I had some trouble with trying to get it to feed. So I've gone through it, had a bit of a look, and basically, in short, what we're going to do is we're going to stay with the notes. I'm going to explain to you why I've chosen to stay with the notes and what it's actually doing. Just because it frustrated me a bit. Shouldn't have really done things off the cuff, but without further ado, let's kick off. So, under Blackboard, I'm going to stay with particular what we're using. So if I go Simulink Notes, I'm going to download my bar linkage, and I'm going to download the bar linkage tutorial. Now the reason I've gone with this, last week we did it with the other group, it worked really well and I quite liked it. So I've now downloaded. What I'm going to do is I'm going to set up a folder on the desktop. Call this bar linkage. Then what I'm going to do is go through to my download. Now I use WinZip. You don't, WinRAR, sorry. You don't have to particularly use anything, but what I've done is unzip them, and I'm going to unzip all these step folders into this single folder. Reason I do this is I want everything to be self-contained, so if I move one folder, that is the job I've been working on. So let's open it up. I'm not going to cover as a remembrances to these, so what I'm going to do is go New and Simulink Model. Let's bring that in. What we'll do is, if you look in the notes, you'll notice that they are, let me just pull these notes up, I can show you. You'll notice from the notes that they are actually in fact alloy steel that we're using. I think I've tried to point it out for SolidWorks Motion here. So it's alloy steel that we're using, and I think, if I'm right, it's 8,500. For those of you who've been in the classroom, that's particular as to why I'm using them values. And what we'll do is similar to the session last week. I'll build this construction, we'll then advance this construction, and then what we'll do is load it and take a look at what's going on. Okay, so the new model started, so I'm going to click on to create blank. Any minute now. Any minute now. Hang on a second. I hit pause just because I was sick of waiting, and that awkward silence is a bit of a bummer. So, got the open blank workspace. Now what I'll do is I'll separate that to there, and I'm going to bring in the library browser. Again, if you're struggling to keep up, please, whenever you need to, hit pause and just get yourself up to speed. As before, we've gone to Simulink. Now within Simulink, I go to Simscape, and this is my operational area here. We are focusing all our efforts to multibody, but I'm going to go Utilities. Within Utilities, I'm going to bring a solver configuration. Now don't forget, this configuration tool just allows me to configure around my present set of configurations that we did. This is when I showed you all how to change from predictor correctors to singular iterative time steps. So it's not a variable time step. So give it a second. It's still, this is the biggest frustration for me. I end up sitting here and waiting and waiting and waiting and waiting. Okay, let's try it again. Oh, there, right. So we've got the solver configuration. Now what I'll do is go to multibody. I'm going to go to Utilities. I'm going to bring in my mechanism configuration. This mechanism configuration is purely because, if you remember, it's all about the gravity. It's what I want gravity to be. So, and then I go to frames and transforms. I'm going to bring in a world frame, and this gives me a point of reference to begin. So what I'll do is line these up, rotate that round, Control and R, Control R, Control R, Control R. So we're roughly now into a position where we have our world set. Now, like last week, I always like to start my builds just to be sure about the operation. So I will first pull bits from here, and then I'll start to move to typing it in, just because it makes life easier. I want a body, And here you'll notice I've got quite a few extra tools. If you install this onto your system, you will end up with the same here. What I'm actually interested in is just a file from Solid, because we're assuming from it's coming from, let's say, some sort of supplier. So what I'll do is, first I'm going to rename this crank based on the original assembly. Sorry, I'm going to rename this frame based on the assembly. Then I'm going to double click in. Once it double clicks in, it brings me up an error and says can't visualize anything. We know that. Can't visualize anything because I can't see anything yet. There's nothing there. So what I'll do is browse to, yeah, still not renamed it, but I'm going to browse to bar linkage and crank. Right, F5, 3, 2, 1. My first point into place. Now, as I always do and always will do, check the frames toggle. That confirms that there is actually one already there, but what I would like to do is have one that I can control. So I'm actually going to place 2 frames, one over here and one over here. First things first, let's get some value onto this, what it's made out of. So I'm going to go not density from file, I'm going to go custom density, and I will go 8500. Whoops, 8500. Click update, it gives me my moments of inertia, center of mass, and mass for the actual component. Press F5, and now we are in business. So, next thing I'm going to start doing is I'm just going to change the color, just because, as some of you will have found last week, it's crazy once you get them all together actually seeing what's going on. So I've randomly chosen that color. I know what some of you are thinking, very feminine, don't care. The last thing I forgot to do, I've clicked apply on that, but I actually now want to add a frame. So I'm going to go frame, new frame. I'm going to click on that edge, come to basis, select apply, and I'll call that back. And then I go save. Do the same thing again. This front edge, basis, select front. Save, apply. Now, because if I click on my toggles, I've now got 2 sectional views here. I'm going to drop show port R because it's no longer used for anything of any constructive value. So I click OK, and now we're in some sort of type of good position. So I've gone OK. Right, now what I do here is I can choose exactly how this thing is going to be mounted, if you will. So let me just bring back the notes. This point here, I can choose where it's going to be, but don't forget, this component really is obsolete. It just kind of helps in the benefit of construction for what we're doing. So let's spin that back round. Then what I'll do is, for a starting component, I think I'm going to bring that to there. That then isolates that particular point. Right, so we know that each point, each interface across the back and front of every single component that we're looking at has a Revolut behavior about it. So go back to my library, and I'm going to go joint, took me a minute then, joint and Revolut. Bring that Revolut in. Now, this is coming to the back. This is going to be the point where the crank interfaces. So I know this one is the golden one. This is the one that will drive. Next thing I want to do is I now want to change to the crank component. So I'm going to right click, drag that over, and I'm going to rename that crank. All the real relations about this stay the same. I double click in, and I'm going to go to here, and I'm going to go to crank 2. F5, apply, check my inertia, it's good. Need to change colour. Colour's going to be a pain otherwise. So let's shift to something more blatantly obvious. I'll go green. Minimize that. And I just need to check my frames. Click on my frames. And if you look, we are in business. Port R's still missing. So we're in good stead. Right, so now we're in a position where technically I can run that, I can check it. So let's run it and let's check it. So I run it. And in a minute, you'll see now it's compiling. So I just got to wait a minute. Wait a minute. two things we need to visit. First thing is, you'll notice now that it seems to be inside, it's penetrating within it. So what we do know is it needs to be moved on its axis, and technically there is a perfect joint between each component. That tells me that gravity is actually acting against it, so in the Z. So in other words, this is like it's laid on a table, so it wouldn't move. Right, 2 seconds. First things first, let's get this gravity fixed. So I'm going to go into my mechanism configuration. From here, I'm going to change that to Y. Bring that in, set that to 0. Don't forget that 0 there. You forget that 0, this thing will not work. It is a Cartesian representation, and it's how it functions. So let's bring that back in, and let's run it again before we make the next modification. So this is good. We've now got that behavior going on. It's exactly what we wanted it to be. So what I'll do is bring it back. Right, so to the next thing we need to do. We need to shift it along an axis. Now, as I was saying to everybody last week, if we're going to shift, one great way of doing this is a rigid transform. So I'll go into my frames and transforms, bring in a rigid transform, drop that in. Bring that back, drop the rigid transform in, just like that. We know the gap between it, because of the notes, it does say it. I know, I've checked. Standard axis, we know that that distance across is 2.5 millimeters. Now, depending on how you've set this up, and as a student noted last week, shall we try and stay with the notes, which is there? So let's just first take a look at that. It depends how we set it. It doesn't really matter. What's important is that the construction sits as our requirements needed. So I've gone to millimeters, because I'm going to shift in millimeters. I'm going to 2.5 millimeters and click apply. If I come back to my model, this is a great tool, by the way, I'll just show it you. I can run it, or I can just click this. This is update diagram. Now you see there, we've now got that offset. Look across, offset's there, it's nice, it's doing what we want it to, happy days. Run it in, and that is exactly what we wanted. So now we're in a position of putting the rocker into position. So I'll slip back, and I'm gonna just come back across here, bring that to there, and because I'm being lazy, I'm gonna bring that over across like that, just because, well, let's face it, I can. Bring that into there, and then I'm gonna rename that to rocker. So now let's get over to the rocker. Now we know from this, we're just going to gradually move along to the next one. Now what I'll do is I'll stay in green, because it's not about having a multicolored solid assembly. If you have components touching, it can be useful to have them joints different colors where the interface sits. So with this case, I can stay green. And in the next one, what I could do is make that one blue or purple or whatever color I've chosen. What we do need to do though is just double check that the frames are sitting correctly. So I've still got back and front. If I click on it, back and front is still sitting there, which is nice. Check my inertia, value still set. Now this is a great thing with this tool. You don't have to mess around too much. So let's reset it again, and then let's run it. I froze then. I kind of thought, why is that not rotating? Go back to the model. I bet you some of you have been sat there going, you silly sod, you've missed a bit. I have missed a bit. So the revolve, it doesn't know it needs to revolve. It just says, well, yeah, I'm doing what you told me to. It's the worst thing with MATLAB. It won't tell you if you're doing something daft like that. So I can be daft, as you may have realised. So I'll click start simulation, and now we're a bit more active like we wanted to. Interesting, look at the momentum between the two. Pendulum theory is really shown here, which is quite nice. I mean, really, if I held it over here, actually on the rocker, and then just let it drop, it would become a triple pendulum, which is your chaos pendulum, which that gets a real misconception as well. But anyway, let's move on. I don't want to get on another rant. Right, so now I'm often unsure what colour I've chosen. I'm going to nick the frame this time. I'm going to change that frame and call it connector. Now, some of you will actually realise that we're almost at the point of what went wrong. Well, not what went wrong, what turned into a bit of a nightmare for me. But when we get to it, I want to show it you, because it's interesting. Initially, the company did set it up. Now, I was trying to really push it a bit, but I'll show you what I mean. First things first, I'm going to connect these up. Now, the reason I'm still doing this particular procedure, if anybody's unsure, is because this is an error that you'll face. It's one of them where you think, I have no idea what's going on, I'm so frustrated, it's driving me insane. Right, so we've got extra faces on here. Those of you who are CAD savvy, if you remember, I was saying that face counts, that's how it recognises where it's going to go. But if you end up with new counts in it, it will either lose a face or attach itself somewhere else. So if I click on my toggle frames, you see there, it's lost a face. Well, it's actually not lost a face, it's actually appearing way over here. So let's get back to back and front. So if I go to front, edit that, and all I wanted to do is just place it here, click apply, save, and then I'm going to add one more here because I want to load it up. I want to see what happens. So I'm just going to put it on there. In fact, I'll put it on the face this time. Oh, I'll put it on the face, click apply, and we'll call that connector. Or mount. Connector mount. Whatever. You can particularly name these whatever you want. I name them things just to remind me exactly what I'm looking at, because when you end up with a very elaborate structure, it gets very, very confusing, as you can more than likely imagine. Okay, so once we've done that, this is what you should get. Which is not a bad thing. Now, a few students did notice, where the hell is it getting this value from? This is just to do with the restriction between the two. You'll notice it hits some particular points and then it returns. And it's just because it's translating from rocker to crank, rocker to crank, rocker to crank. This is because it's ideal. So all this, there's no friction between the bearings, so it will just keep tilting like that. So what we need to do is we need to now shift this, and we now need to look at how what mistakes I've had or made. Now some of you will be thinking, well, we did this. I mean, I know I did this, but I want to cover that because it's important to keep these things in mind. So I'm going to right click, I'm going to bring across another rigid transform there and there. This is purely because, don't forget, we had a 2.5mm offset. So I'm going to run this again. Now so with me doing that, if I run this across, we should find that we're actually now looking pretty good. So if I come back to my model, we are now in position. Now this is quite nice. I was hoping to get to this very, very quickly, which we have done. These particular areas, now what I was trying to do is I was trying to actuate this joint just to see if I could really push the boundaries of what this joint could do. I got to the limits, bit of a frustrating thing. So what we'll do is we'll set it as I wanted this thing to be set. So what we're doing is we're actually not driving any actuation at all. I'm leaving motion to be calculated, because what I'm going to do is I'm going to set my targets. Initial position, I'll set that to 90 degrees. Target velocity, I'll set that to, now this is where it might crash because I'm trying to set two particular points. It's good, but it comes at a price. So let's go, let me just double check the notes. I don't remember what value we should be set at. 3 minutes, 2 minutes. We'll get there, we'll get there, we'll get there. My goodness. There we go. That's what I was looking for. So where are we? Where are we? 60! We've got 60 revs. I just needed to be sure. So if I go 60 revs. Now what I've done is I've added that target position. This is where I'm not sure how well this is going to work. I may need to drop it just because I'm trying to position it and drive at the same time, and this is where the system might go, I prefer to have one particular drive if you don't mind. So what I'll do is I'll set my initial target time 0.017, and then let's just see if this runs as we want it to. So let me bring this joint back and let's just get it into a rough position. Then let's just drive it. Oh, that went really well. Really well. So, why it didn't work then? I kept running play, and this is just a reanimation of what was done before. So to run it, you want to run it from the home and make sure that everything's rebuilt and reassigned. So if I run it now, if I run, kind of comes to there. Now that's where I'm a bit unsure as to what's going on, so I'll just slow things down and run it again. Ooh, look at that. So if I spin it, slow it down even more, time sped here, and then run it again. Now what we've got is something a little bit more appealing. So bring it back round. You see there, starts at 90 degrees and it executes. So this is nice news. So it means that we've got an operational system. So our system now runs. Nice. So let's bring this back, and then now let's start trying to mess it up a little bit, because a lot of these things are really great, but what's important with this is it's important to be able to apply forces to it. We want to look at what's really going on. So first things first, what I'll do is I'm going to apply a tool that we've not really touched yet. I'm going to go to forces and torques, and what I'm actually after is external force, unless they've renamed it, knowing my look. No, they're not. External force and torque. I'm going to drag that in. I love this. So I'm going to tab that in. The reason I've been jabbering on, and I know I jabber, about gravity, knowing where everything's sitting, is we need to know where our gravity sits, because we need to know what direction the connector is holding on to it. So I'm going to double click in, I'm going to go force, and I'm going to go Y. So apply force in the Y component. Now it says, okay, you've got that force there. Now what do you want to do? Now we're going to have to drive it with something. So we come back to the main system, and what I'll do is go to utilities again. Now I'm going to go Simulink to power stream converter. Don't know why they call it the power stream. So I'm going to go power stream converter. Tab that bad boy in. And like as ever, I always like to be sure. So let's make sure them units are in the right units. So we'll go N. Because in the notes we're suggesting 88.96 newtons of force should be applied. And what I'll do is, there's a few things I can do. In the notes I added a constant value. Now just because I'm curious as to the whole process, I'll go signal builder. This is I love doing this. So let's bring that in, tap that to there, and tab that in. Now what this is going to allow me to do is to only load it in certain states if I wanted. So let's double click in. That's over 10 seconds. Shit. So what I'll do, I'll let you play around with changing this, but I'm going to change that and just put it like that. Yeah, delete that. And with this, I'm going to set that to 88.96. So if we go Y, 88.96. So this would suggest that the system will be continuously loaded. If I wanted to unload it, so it starts off at that value and then unloads it, we'll do that in just a second. So let's run it. Bring it to there, delete that, bring that in. Boom. So if I run it, behavior operates the same. So what I'm going to do is go into here, I want to know what level of torque it had to put out to be able to deliver something like that. So what I'll do is I'll come down to my actuator sensing, and I'm going to go actuator torque. It will tell me what it needed to be able to do that, and that's where I'm really curious. So what I will do is go back to my SimScape again. I'm going to bring in a power stream to Simulink converter, because now it's not about that way, it's about doing it the other way. So let's bring that back. Bring that up. Now we're looking pretty good. Now obviously this is in Newton meters. I'll go, what I'd like though is a scope. I'll stay with one port for this. I just want to see what's going on. Let's bring that into there. Now this is a real curious one. You'll really like this. So let me just stop that. And then let's run it again. So bring it in. Come on, double click. Wow, this irritates me sometimes. And you come back and go, well, where is it? What's going on? So you come back and go, that just doesn't make sense. The actuator, the sensing of the actuator torque can be very misleading, because what it will do is it will tell you the initialized torque coming from the actuator. It's a huge pain in the backside. So because I can feel somebody saying, well, what's the difference? This is my point. We've run it and we got nothing, because there's nothing driving to it. We want to know what the whole thing's going on. So I'm going to go total torque. We can go constraint torque, but we'll go total torque. This is everything in the active area. So if I run it again, boom. What we're now in a position of is looking at exactly what's going on. Now look at some of these spikes within it. We would need to tighten up the steps on this. Right, so if I come back to this, check this out. So it's suggesting at, whoops, around here is some of the highest loads. So that curve, we end up with a spike here. This spike is about 38 Newton meters. 38 Newton meters! 38 Newton meters! Well, Newton millimeters it should be really, because that's particularly what their value have been working to. Interesting, very interesting. What we're going to do is then progress it. So let's just close that. Not happy with that output. First things first, I'm going to go to my... They moved everything around. Really annoys me. I'm going to go to my... model settings. I'm just going to juice up that iterative time step, you know, on the predictor correctors. So I'm going to extend here and change that to my relevant tolerance. I'm going to make that a little bit smaller. We'll go 0.5, 0.0005. Run it again. Now let's take a look at that output. Still very, very clunky. Is that we could keep tightening and tightening to make that a little bit more smooth, but yeah, I mean, look at this, right? Because I've tightened, I've given it more time steps to look at. It's actually spiked even higher. Very interesting. Now the thing is you don't know if it's the steel or if it's the weight. So this is where using the signal builder becomes a real benefit. There we go. Right, so we've now constructed it, and we've now dropped the linearized load straight onto it. But what's the benefit of using constant value as opposed to signal builder? Signal builder in this case is great. We can have multiple choice between each offset. We can choose all different directions, and it's great for what we need it to do. So what I'm going to do is I'm going to try and restrict my T value. So if I go to change time range, see how it goes to 10. What I'm going to do is set that to 0.017. Click OK. And now look at that. That is the overall time period. So we can do a few things. We could potentially ramp this up, so gradually build it up to that weight. Or we could look at it at a 0, or we could look at it as when it rises. Now I'm going to add a signal to that, which is more like this. So ironically, I'm going to actually delete this one out. I don't need it. And I should actually remember what that value was. So if we go on to here, I've got a value of 88.96. What I'll do is increment it halfway through. So I'll left click onto here, and we're going to go Y being 88.96, and then run. So let's look at the component in action. Now you look there where it's gone right up through the roof for as far as its delivery, and what I'm going to do is I'm going to attach that on, and then run it again. Let's see what it does. Look here, we've got this spiking. Now the first and the second, this refers to the torque and reaction torque that's going on. See, if I come back onto my constraint onto here, so this is total, but if I come back onto my constraint here and then go to sensing again, scroll it down, oh, not sensing, so we're going to total, but if I go constraint force and then remove my total force, run it again. Now this is responding around the typical constraint that I'm given. It's ace bit of kit, really is. But you can see there with the level of torque that's coming in, it's around 40-41. I'm going to try and tighten up my time step with it, see if that does it. So I'll raise that up. I'll go even more crazy with this. I'm going to go to the power of 9. Run it again. Now look at this. We've got an initial output. Look at that. We have what, 12 Newton meters on this particular torque. We have what, 42 Newton meters on that particular torque. Now this is the spike of when it becomes loaded, so there's force that occurs within it. So that would suggest to me, if we bought a motor which operated around 25% greater, so if we went for something like, just off the cuff, if we go for something like 60 to 80, if we went 80 Newton meter of torque for this particular body, we would be in a good stead. So if you want verification for the notes itself, I've offered some verification as well. Let me just find you the verification. We can track particular spaces. Let me just find my verification model. We check here, we have this verification, and we can pull out around 59.1, but that was me operating on the 88.96. So am I at 88 I don't even know if I'm at 88.96 there. I think I am. Yes, 88.96. So by Y, by X, we've 31.88, and by Y we have 59.1 newtons acting in each particular area. Sweet. Okay. Right, so I hope you found this a benefit. I hope this... Sorry, I was just having to think about that then. I hope you found this a benefit. What I was trying to do, what messed things up a lot, is this joint here. I was trying to get it to operate in another particular range. If you want to play around with looking at what would happen if the joints were damped, if there was a coefficient of friction restricting that joint, try it within here, look at particular coefficient of frictions and drop them in, see what type of an impact it has on it. But that is the crank, well, the 4-bar mechanism, the bar linkage system, whichever way you want to look at it. That is an overall working value, overall working model of it. I hope you found it, again, I hope you found this a benefit. Just looking at anything else that we could add to this. And I will see you all very soon.